Okay, so we are looking here at the last section from chapter 4 and actually for unit 1 that we're going to be covering. So we're looking at different types of properties for solids that exist. So when we say something is a solid, of course, we have generic properties that we think of when we, depending on what solid kind of pops in our minds, right? So really the goal of this lesson is we're going to look at over the different types of solids and kind of what makes each one a little bit different from each other. So the first one here are ionic solids. So these are basically solids that are composed of from ionic compounds. So all ionic compounds create a solid at room temperature. So under SATP conditions, so standard ambient temperature and pressure conditions, when you have electrons that are being gained and lost between elements, typically we have a metal with a non-metal, you're going to end up having a strong connection between the ions that result. So the positive ion and the negative ion, and the negative ion is typically larger because of the electron affinity that exists here. So what ends up happening is you have, and the shielding, I should mention. So here we have the attractive forces are very strong, right? So opposites attract. So the term for this attraction actually does not follow intermolecular forces. This is called an electrostatic attraction. So that just goes down to the basics of opposites attract and like charges repel. The positive and negative ions essentially are attracted together because they have opposite charges. So because they are so tightly packed together, so this picture is showing you there is some distance between them, but this is just to mimic you the shape that it will take on. You end up having this crystal lattice structure. So essentially it's alternating ions. So you have positive, maybe you can't see that well. Right, so positive, negative, positive, negative, positive, positive, negative, positive, negative, positive, negative, positive. So basically you have this cube that's alternating positive and negative ions, right? So imagine if you were to start doing this, here's in like the simplest way. Right? But then this will take on a cubic structure, right? So the term for that is a crystal lattice. So this electrostatic force is actually stronger than any intermolecular force that we had looked at before with non-metal molecules. So ionic solids are stable and they have, in comparison to non-metal molecules, very high melting temperatures. So ionic compounds always have a higher melting temperature in comparison to non-metals or molecular solids. So when you're looking at this, the other factors that are to consider here is, ionic compounds are also conductive when in water, right? They also are, that's again, all of this results because of the ions that exist there, right? So it's able to conduct when in water. It's important to know that's not as a solid. So solids, ionic compounds in the solid form do not conduct electricity. It's only when it is aqueous because you need free-flowing ions. So the term for that is that they're considered to be electrolytes as well. Okay. So the next type of solid is a metallic crystal, or sometimes we just refer to this as metals. Metals are solid, other than, of course, the exception to that is going to be liquid mercury. But every other metal at SATP conditions is a solid. Okay, so it says here, funny enough, it says metallic bond. Okay, so really what's happening is the metal atoms are not bonded together. But what happens is because they're so compact, the attraction between the atoms of a metal are so strong, they're so densely compact, is what happens is the orbital spaces actually begin to overlap with each other. So, let's say here we have a bunch of metal atoms. The orbitals are so close that basically the electrons are able to flow freely between any of these atoms, which leads to the main property that we think of when we think of metals, I'm hoping anyway, is that they have the ability to conduct heat and electricity. It's because energy, and remember, electrons behave like energy, they move like energy, so why wouldn't other types of energy be able to move through it? They're able to basically jump from atom to atom very, very quickly. Okay, so metals are malleable and ductile. So part of the reasoning for this is because you don't really have a rigid bond structure here. You essentially have atoms that are closely compact together, but they're not really bonded. There's no bonds to break. If I want to stretch this out or make this into a different shape, you can do that because you don't have to break bonds in order to do so. So it can be done. I mean, obviously you'd have to heat them up. They are very, the melting point is very high in metals, but you can do that relatively easily. You're not changing the actual substance. Okay, molecular crystal, in other words, a non-metallic solid, okay, is where you have a solid compound composed of only non-metals. So non-metals come in a variety, like non-metal molecules, you have a variety of different states of matter. So what we're referring to here is where you have a solid made solely of non-metals, and actually more specifically, typically we're discussing non-polar ones as well. So you can have polar molecular crystals or non-polar molecular crystals, of course. So by comparison, the non-polar is going to be much weaker in comparison to the polar, for the reasons we talked about in intermolecular forces, right? But if we were looking at non-polar weakly held together molecules that are solid, such as iodine, right? So iodine is non-polar. It has only LDF. So when you have a solid structure, it's actually pretty weakly held together. So meaning you could probably crush this with, a stir rod in a beaker. If you had a chunk of iodine, you could probably just crush it like that, or a mortar and pestle. So you don't need to have, you don't need to melt it down in order to change the shape. You can actually crush it into a powder really easily. Of course, polar substances are a little bit stronger, more tightly compact, but you will still have the ability to do so. So in terms of melting points, right, this will have a very low melting point. Polar molecular crystals will have higher compared to the non-polar ones, but still much weaker compared to the other two beforehand that we just mentioned. So like this would still be lower than ionic for sure. And the last type of solid is known as a network solid. So these are covalent structures, so meaning these are still composed of non-metals, but these are a little bit more unique. So these are non-metals that when they come together to form a solid, they create a specific pattern to how the atoms are interconnected or interacting, I should say. So what ends up happening is the properties kind of vary very greatly here. You can have a difference of something very weak to something very, very high. Sometimes they're going to be brittle, sometimes they're going to be incredibly hard. So it depends on the pattern that you're discussing. So all three of these patterns that I have here as an example are composed of exactly the same thing, solid carbon atoms. So carbon can take on different orientations depending on what type of network we're looking at. So graphite is the same as your, think of your pencil lead, if you have a pencil that takes the lead to write with. So graphite is very, very brittle. right? If you've ever tried writing and put a little bit too much pressure on your lead pencil, you know that it will break very easily. It snaps very easily. That's because even though you have a network, the network is actually not very large, especially if you compare it to these other networks we're looking at here. So we have, 5 different atoms. They take on the same structure and they lie on the same plane. So what happens is they kind of lie on top of one another like sheets of paper. So it's kind of easy to break them. It's very brittle because, all you need to do is put a little bit of pressure and you can crack it right in between one of those layers. However, over time, with pressure and heat, of course, changes within the structure over time, we can start to have more complex networks, such as a diamond. So this essentially will lead to this. So diamonds is the example, right, known as the very, very hard substance, the hardest naturally and made. Okay. So the hardest naturally known substance currently. So this pattern that it takes on, obviously, if you look at this, is much more complex, much tougher to break through. So over time, right, not only do you have network patterns, but the pattern can also change over time. Now, a buckyball is not something that diamonds will turn into. This is actually also made up of carbon atoms. So what it is it's 60 carbon atoms that create this spherical form. This is actually used quite a bit in research and development in many different fields of science. Anything from cosmetics to, Xerox looking at different types of ink formulas. So buckyballs we don't really kind of use them in everyday life. I mean, like you would your pencil lead. But I just wanted to show a different type of configuration and pattern. So most network solids involve carbon. Okay, the most common ones are carbon. On a screen here. Carbon and silicone structures. Okay, more specifically, silicone oxides. Okay, I'm going to put a little X here because it can be silicone dioxide, silicone tetraoxide. There's a whole bunch of variety of silicone oxides and silicone based solids that can take on different types of patterns. Okay, now in terms of the silicone oxides, and of course, if you're talking about carbon in the diamond form, they are very, very strong, not very malleable at all, because the melting point is actually very, very high when you're looking at these more complex patterns. Okay, so I don't really expect you to know the ins and outs of this. You're not going to be drawing these patterns for me, but you should be able to kind of compare the different solid types to one another based on their properties.